So the point of this exercise and the video is this is my Bike Friday. It's a electric assist touring bike, and I want to have the ability to, it folds down and fits in luggage, and I want to have the ability to bring my lithium ion battery with me and go and tour in different locations. So researching this, I've looked at what the regulations are for the TSA and the FAA. And at first glance, it doesn't, I can't take a standard e-bike battery. It's just not an option. Similarly, I checked into United States Postal Service, UPS, and FedEx, and those do not seem like options either. I cannot go to a local shipping center and ship a battery ahead. It requires a Class 9 hazardous certificate, which I do not have. The only way the manufacturers get around this is because they have that certificate and that certification to ship that battery and to package it. Unfortunately, as a consumer, I do not. And if you do some internet searches, if you get caught shipping a lithium battery, you can be fined some pretty big money for it. So that doesn't seem like an option either. So the objective is to play by the rules and to figure out how to overcome this scenario. So researching the requirements for lithium batteries for air travel, I've gone to TSA.gov travel and looked up their actual rules, and they have a category of lithium batteries with 100 watt hours or less in a device. And it basically says that you can carry in your carry-on bags only, not checked bags. And basically it says that the spare uninstalled lithium ion battery or lithium metal batteries, as long as they are limited to a rating of 100 watt hours per battery, that they're acceptable. It says that this covers spare lithium metal and spare rechargeable batteries, which we will have, for personal electronics, cameras, cell phones, tablets, watches, calculators, and etc. We're making a battery pack, but we're not going to have it assembled. There is another category for batteries over 100 watt hours, but it requires the approval of the airline, and unfortunately it caps it at 160 watt hours, which is not really that much larger. Okay, and similarly, going over to the FAA.gov, hazmat, pack safe lithium batteries. Similar, it looks like a lot of the language is exactly the same, that the TSA has adopted the FAA's, but basically it says that spare uninstalled lithium ion and lithium metal batteries must be carried on carry-on baggage, which is the same. It covers the spare lithium ion batteries such as cameras. It has the same tablets, watches, etc. So we fall under that category. This size limits say that the lithium metal can go all the way to 100 watt hours per battery. It says these, and here is the wonderful thing, is the quantity limits right here. None for most batteries, but batteries must be for use by the passenger. Batteries carried for further sale or distribution are prohibited. And then there is a limit of 2 spare batteries, but that's when you step up into that 101 to 160 watt hours per battery. So we are going to stay at 100. This is the existing 36 volt, 12 amp hour pack that I have for my Bike Friday. This pack on my Bike Friday gives me about 55, almost 60 miles of range. It is a typical pack of high quality cells. It has a built-in BMS, and that's what I want to discuss about this. The idea of recreating this with individual packs is going to involve not having a BMS. And so I guess we first need to have that discussion. So let's talk about the two primary functions that the BMS provides. The primary function is a safe way to charge the whole pack at one time. In the case of the battery pack that I intend on building, that function's not necessarily needed because I don't intend on building a pack and charging it as one big pack. I intend on pulling these out and charging them just like you would for your cordless drill. So that function of the BMS I don't necessarily need. I think the most critical part of the BMS function would be the low voltage cutoff. The bike controller itself provides low voltage cutoff, and for my specific bike, it is at 30 volts. So this is a 36 volt pack. Once it reaches 30 volts, my bicycle controller will stop trying to draw power from this. Similarly, this battery itself has built in the BMS of low voltage cutoff. So my plan is to not try to incorporate a BMS, but instead just build the battery pack. Its nominal voltage that it will charge to will be around 41 to 42 volts. Its nominal voltage is 36, but its top voltage 41, 42. And I will set a cutoff because I can see it on the display of my bicycle. I will set the cutoff and not use the controller that's on my bicycle as the cutoff. I will just say that when I see 31 volts, I will not go below 31 volts. What happens if I go under 31 volts? I run the risk of taking this battery below its ability to recharge again. And that's the risk that you run with these batteries. You know, will it catch fire? Not necessarily. Most likely, I'll just kill the battery, and then when I go to plug it into a DeWalt charger, it will have so low a voltage, which I think is right around, for these packs, it's right around 14.1. You take it below that, the charger won't recognize it that it's a battery and won't try to charge it. So that's what we're going to try to avoid, and I'm going to do that by just setting my voltage cutoff at 31 volts. So the battery of choice is a DeWalt 20 volt 5 amp hour pack. That combined together, 20 volts at 5 amp hours, is a 100 watt hour battery. It's actually a little less because the 20 volts is a misrepresentation on DeWalt's behalf. It's an 18 volt pack at 5 amp hours. And the idea is if I take two of these and run them in series, then I will have a total of 36 volts at 5 amp hours. If I take those and run them in parallel with another pack, then I will total out at 36 volts, and it will be a total of 10 amp hours because of the parallel. We're going to be using these 3D printed battery receivers, and that just have a positive and negative terminal that interact with the battery. And the nice thing about them is they're 3D printed with a lock system here. So just here, you gotta keep these wires separate while we do this, but we can slide it together. There's that positive clip that it's locked in, it can't be removed. And at that point, we end up with 20 volts, 5 amp hours at the end of these wires. So the idea is that we'll take a total of 4 of these to build our pack and lay them out in something that works best. I've kind of played around with 2 different ideas that I like. I like this idea, 2 slide in and the other two slide in like that. So I'm kind of looking at a pack size maybe like that, where there would be these kind of like that, and I could wire them together. The other option, kind of deciding against, would be just to line them all up like this and plug them in. Boom, boom. That's certainly an option. It's just. I think I like the fit and form factor of this much better. Like that. So thinking through it some more, I like this idea. What I could do is lay them out on each side like this. This battery would snap in here. This battery would snap in there. That would be on this side, and then it would be duplicated on the other side. I like that idea. Also like the fact that the red positive terminal from this one is lined up with the black, because that will give us our series connection. So that'll be the series, and then these two, red and black, would reach over to meet the other side, and we could join them together in parallel. And then that would be just adding, that would just be increasing the current capability. So I like it. So now I just need something to mount this to. I've chosen a piece of plastic 3/8 thick polycarbonate composite, description in the, or link in the description, and I think it's going to be easy to manipulate. I can run it through my saw and cut it to width, mount these on here, and easily drill it and join them together. And then, as I was talking about, flip it over and do the exact same thing on the back side, and then I'll have a fairly small footprint for this battery pack. As for attaching these, I think I like the idea of bolting them like a sandwich. So it'll be the battery receiver, the plate, and then another one right on the other side, lining up on these three holes that are on the 3D printed battery connector. The only problem that I see is the counter bore is not large enough to put a nut, and nothing can protrude above that surface or it will interfere with the battery sliding in. So I searched around and found some sex bolts that basically are a cylinder and a shank and then a small threaded bolt. And the idea is that I can use these and they'll drop inside of this counter bore and fit inside. The only problem is we've got a little bit of misalignment. This is about 185 thousandths on the diameter, and I want it to pass through these holes that are on this piece here. And the through hole is about 170. So I need to take a drill, open these up just a tad, 10 thousandths in diameter, and then I'll be able to drop this through, all the way through. It'll go through the board, and this bolt will screw into the back side, and you can use Allen keys to tighten the whole assembly together. So let me go ahead and open these up to roughly something that's just something that's a little bit bigger than this, which is roughly 187, so about 3/16. Let me open it up to 3/16 so they'll drop through. Yeah, that's perfect. Okay, now I'll just trim this black polycarbonate down to something that will hold basically these two like that. So maybe something like that. Cut it right about there. I'll set up the blade about the width of the battery receiver. We'll cut it there.
Okay, so this is what I've ended up with, small piece like that. Go like this. That's kind of the idea about like that. I'll go ahead and mark these 3 holes, drill them through, do the same here, and then come back and we'll try to bolt the whole thing together using those sex bolts. Okay, just a quick assembly to make sure this is going to work. So insert the sex bolts into the countersunk holes. Just do 2 at a time. There's the holes. Oh, it's perfect. Okay, and that gives us just enough sticking out on the other end for the mating one to line up with it. Let's see if that works. Yes. And that gives us just enough for the nut, or for the screw on the other side. I think we got a winner here. This looks like it's going to assemble together real nice. This will be duplicated on this side. Those packs will sit just basically like that. And we'll have a fairly compact little battery system. Okay, just a quick mock-up with these in loose to see how things are going to shake out. As I mentioned previously, this is where I'm going to make the series connection between these 2 battery packs. So I'm going to take the negative from the one and join it to the positive, and then the other 2 leads are going to come off, and we'll join the other 2 leads from the other side, and those will actually be parallel connections where the black goes with the black and the red goes with the red. Just looking at making this connection here, many options. I could solder it, I could mechanically bind it. I think just since it's so close and I don't really want to work in there with a soldering iron, I think I'm going to possibly do something like this, where I just mechanically bind them together and heat shrink it. Okay, so just thinking out loud here, just looking at how I'm going to mechanically install this crimp. Looks like it's going to be just between the 2. So I'm going to mark each lead right where I think it will end. Cut it and then assemble this back. Okay, I'm going to cut it on my mark. And I'm going to, let's see, strip back about half of that. This is 10 gauge, so just come right about there. There it is. Looks good. Now I'm going to do the same with this side. Strip it back, it's 10 gauge, about a matching amount. Then I'm going to do a quick test fit just to see if my links that I cut these are close. Because I don't want to switch this thing or crimp this together and then realize it's not close enough or too far away. That looks pretty good. Just that, and then I'll swedge that right in the middle of the 2. Okay, I'm going to start with this side here. Make sure that's seated all the way down in there. Use my crimpers. That looks really good. dry run test fit, see how that's going to line up. Looks like it's going to be a little tight, but we can take care of that. Okay. Trim just a tad off this because it looked a little tight, and expose a little more insulation right here just so we can, there. Tell you what, I'll trim a little of this off as well, so we get a really good mate. Perfect. Okay, I'm happy with what I've got. The mechanical crimps went really well. It's nice and secure. I think we got good contact. Gonna go ahead and heat shrink this connector down, and then we'll flip over. I'll flip over and do the other side, matching it identical. Okay, working on the other side, doing the exact same thing, just cut the positive and negative, same thing. These leads will go over in parallel on the other side, like what I've got here, and then I will do a connector, mechanical connector between the two. Okay, gonna go ahead and give it a test assembly and see how well this is gonna work out here. Let's start. Let's do one screw at a time. How about that? Beautiful. All right, so that's the single one in, and we'll go from there. So working on the other side, I'll just add one of these small plastic black washers under the head of the sex bolt and replace it that way. Give me a little more bite and grip to pull this thing together. Yeah, so the plastic washer under the sex bolt is definitely a perfect situation. It just gives it just enough distance that the sex bolt will tighten up real nicely on the whole assembly. It becomes very, very secure. Okay, perfect. This thing's looking good. Okay, that worked out really good. I ended up going and adding a black washer under each side of the sex bolt. It felt much better to draw it really tight. Now this thing is super sturdy. So we're looking good. We've got our series connection coming up on this side, and the same series connection on this side coming up. And the idea is we'll join these two red wires and these two black wires, and we will see 36 volts at 10 amp hours. We will have a nice pack just gonna do a test fit, and I realized that I have to be careful with these leads when I go to plug these in, because it does become live. What a nice looking setup that is. And as you can imagine, this side over here is going to be like that. Not sure if you can see that, but that is a sweet looking little battery pack. So for the connections, I know ultimately what I want to come out of this is I want these two positives to come together. That's going to give me 36 volts positive, and here's the 36 volts negative DC. So that's what I want. I've decided to do it with XT60 connectors to make it kind of modular in fashion. So my thoughts were, this is something you can purchase, and it's a splitter. I kind of like the way this will lay out. Basically, you have two females and each has a positive, so I can join these two positives to one side of a connector and join these two negatives to another side of a connector. So you'd have two connectors plug in, and then it comes to a single source, which I should be able to read 36 volts at that point. The other nice part of this plan is if I do that, then there are many options for compatibility with my bicycle. My Bike Friday uses a small Anderson connector, so I found this online. XT60, that will give me this combination. And then this will connect to the battery pack and give me a nice long lead. So the method that this will occur is I'll be soldering on these XT60s to these leads. So I will separate this like this. And on this lead, the square side is the positive. So the positive will be soldered on here, and the negative will be soldered on there. And I'll duplicate the same process on the other side, plug in the Y splitter, and I'll have 36 volts DC at 10 amp hours at the end of this. Okay, so soldering, I'm not going to claim to be the best solderer, but I'll show you what I know, and I'll show you what I know works. The best thing to do is get your work in like some magic fingers. Let me get this in view here. And this is just the connector, and all we're going to do at this point is just fill these little cups with solder ready to receive the wire. So you're going to do that step first. So get you some magic fingers or something that will hold that. This is just soldering paste or soldering flux. It just helps with the solder actually sticking to these gold tips. And our goal is to put a little puddle of solder inside that cylinder. Get yourself a soldering iron that you can, it doesn't have to be super expensive. This one is like a $20 special on Amazon, and I've set it to 480, the highest temperature. One of my best recommendations for soldering is make sure your tip is clean. I sanded this with sandpaper before I heated it up, and get a good solder that just kind of works with your tip. Better view of soldering one here. Set it in there, let the heat start to transfer to the connector. Get the solder ready to flow once the connector heats up. It'll all kind of happen at once. There it goes. And then fill that cup up, let the heat pull it back across. So I've trimmed all these wires, and I'm getting ready to connect them to the connectors, but before we do that, we're going to tin the end of the wire, and that means to just add a little bit of solder to it. So see if this is in focus. I'll start with this little one here, and the best way to do this is, there again, just hold the soldering iron up to it. Let a little bit of heat transfer happen. And I'll tell you what, just to make this a little more simple, I'm going to secure this wire with an alligator clamp, and that'll make it easier to hold. And it's just there it is. Heat transfer's happening. There you go, and it flows in there nicely. Like that, nice and tinned, so that solder actually sucks back into the wire. So I'm gonna do that with the remaining ones, and then we'll go ahead and make them. Okay, getting things ready to solder together. So this is the connector. This is actually a cover that goes on it. So avoid the rookie mistake and go ahead and put these covers on now so we don't forget them. We'll just slide them down at the end, and I'll do it on both sides. Okay, so for soldering, I've placed my connector inside a clamp and pushed it down against the table. And since this is the negative side of the connector, my plan is just to hold the negative wire right on top of that little pocket and apply my heat and just push down the whole assembly right into it. So the trick with this is get in with the heat and get out so you don't melt wires or burn your fingers or any of that stuff. So let's just get this. I'll come right on top. You'll feel it when it drops into the pocket. Just like that. It'll drop into that pocket and the solder will flow back up and make a nice joint. You want to let it cool for a second, and then you can release it. And now you've got a nice little joint there. Okay, here comes the fun part, and that's to test to see what we did, if it works right. So my plan is just on this one side, take battery, install it on each side, and measure here. I should see 36 volts because I'm adding the two 18-volt batteries together. And I should also see the polarity, that this is positive and that's negative. So that's the two checks I'm looking for. These batteries aren't fully charged, probably 50%, but enough to test our setup. So with my multimeter set to 200, I'm gonna attach the positive to the red to the positive. I'm seeing 36.7 volts and the polarity is correct. So that's a good test. I'm gonna flip this over and test the same on the other side to confirm that I've got polarity correct there. 36.7, 36.8 volts there. Okay, so now I know I've got 36 volts here and I've got 36 volts here. This is where we're going to join these two together, and that's this splitter. And we know that, let's see if I can get this correct. So red to red, that's perfect. And then same down here, we're gonna spin this around, red to red. Okay, final test should be snap in all the batteries. I know that I'm not dead shorting anything, and pull around, and I should see, again, 36 volts here. And with the combination of the 4 batteries, 2 in series, 2 in parallel, I should have 36 volts at 10 amp hours, which is a nice battery pack. So let me give that a try real quick, just for the final check. Cool looking battery pack. I like it. That is perfect. Put this in a rear rack bag and fish these leads out, and this thing's going to be awesome. All right, so final sanity check on my connector. I should be seeing 36 volts here. Let's do this without shorting the battery. There's the negative. There it is. It's 36.3 positive volts. And just for sanity check, I'll go backwards just to make sure that I don't have the polarity incorrect. And there's a negative 36 volts. So we have got a pack that we can go and test. We can charge the cells, snap it all together. Really like how this worked out here. This looks nice. Like that. I really like it. Okay, with the complete pack, I bought a cheap rear rack bag. It's got straps that'll just fit on the back of my Bike Friday, strap right to the rack. And let's see how this works. This is perfect. Absolutely perfect. So the batteries fit just perfect in there. They're nicely protected. There's plenty of room for them. I'm going to go ahead and leave just this side out. Zip this around. And there you have it. You've got a TSA approved 36 volt 10 amp hour battery pack set up with an Anderson connector to drive my Bike Friday. And I'm going to go out and give this thing a test and see what it's capable of doing. This is going to be a really cool setup. My plan is to, as I go through TSA, I will set these 4 batteries on top of my backpack. I'll pull them out, set them on top, let them see that they are DeWalt batteries, that they are 100 watt hours, and that they meet the FAA and TSA's requirements. I'll keep them on the outside of the backpack. Inside of my backpack, I will have my battery kit. There's nothing that should not alarm anything. All it is a set of wires. Shouldn't be any issues there whatsoever. And it's really none of their business as to what I'm going to do with these batteries when I get to my destination. So I think this is a really cool setup. I look forward to flying with my battery. And here you can see the final product. This is my Bike Friday, and I've mounted my battery pack, which is in that rear rack case. It mounts nicely and just ties right into the speed controller. And I have a 36 volt system. It's 10 amp hours. I've taken it out. I've done over 40 miles with it so far, and no issues at all. I've charged the batteries, I've run it down, charged the batteries back up. I've stayed above the 31 volt threshold. I've actually stayed above 32 just to be conservative, but it works excellent. And I just come home and charge all the batteries back up, snap them all back in, and off I go. So in conclusion, I hope you found this video useful. I hope that you're able to make your own travel TSA approved battery pack. And most importantly, I hope you're able to take your bike on many awesome adventures. Thank you for watching.